Okay, we're going to be doing an intramolecular Aldol condensation. So for this reaction, we're going to be doing an Aldol condensation inside the molecule itself. Like in the other examples, it would be attacking like a different one, or I guess. So okay, question is, so we're going to have hydroxide and he's going to be attacking something. Question is, who is he going to be attacking? Because I see two alpha carbons. I see an alpha carbon here, and I see an alpha carbon here as well, and they both have high like alpha proton. So who is he going to be attacking? So question comes down to, this functional group is called a ketone, and this functional group is an aldehyde. Now you have to figure out. No, I'm not even going to say all that. Aldehyde is more reactive than a ketone, because if you look at a ketone, he has this group here and he has this group here, and that's blocking access. The aldehyde is basically a ketone, but that methyl is now an H, and H is easy to attack. So it's basically just less things to attack. So that's why aldehyde is more reactive. So this is why we're gonna put we're gonna put a lone pair on. We're gonna put a lone pair on this alpha carbon next to the ketone, so we can then attack the more reactive aldehyde. So I'm gonna get rid of that alpha. I'm gonna just put it right here. I'm gonna put alpha here. Okay, so we want to attack the aldehyde. We don't put it here because if we put it here, we would be attacking the ketone. We don't want to attack the ketone. We want to attack the more reactive molecule. So the first step is acid base. And even before all that, since we know what we're gonna do, like if you look on an exam question, the question's gonna look like this, right? And if you see intramolecular, that means we're gonna get a cyclic molecule. And if you have a cyclic molecule, before you even do any of this, like before you even do the mechanism, it's important to count how many carbons are gonna be in the molecule, right? So you start counting. Um, you start counting from here. 1, 2, 3, 4, 5. You're gonna stop at the ketone, or you're gonna stop at the molecule that you put the. You're gonna stop before the molecule that you put the negative charge on. So now that we made that, right, we have a 5-membered ring. It could be 6 or 5. Obviously, 6 is a better ring. 7-membered ring is more bulky, and 8 is also like bigger. So that's why 6 is the best. 5 is under, which is better. 6 is obviously better than 5. My point. Okay. Yeah. So now we're gonna have this molecule. We're gonna have a negative charge right here, and we have an extra. We have a. This is alpha. He has a hydrogen. It's gonna come in handy later. So this is gonna attack. It's gonna do nucleophilic addition on here. It's gonna put the charge on oxygen or whatever. It's gonna make. We're gonna make oxygen negatively charged. So now we're gonna form some cyclic molecule. It seems complicated because we're making a freaking like shape and all that. It's just remember how like primary school, a pentagon. Okay, 5 is a pentagon, so just draw a pentagon first. So I'm gonna draw a pentagon. That looks like a pentagon, right? And then just like number it. Well, I don't know why I'm using red for everything. Okay, 1, 2, 3, 4, 5. Okay, and so now we're gonna have this. I mean, draw the H, right? And then this O has a negative charge, and this has a ketone, right? This has an H, and this is the ketone. Okay, make sure you write the alpha. You don't want to forget which is the alpha carbon. It's gonna come in handy later. I mean, in like one step. I'm bugging. Okay. Um, Now we formed in the first step. We formed water, right? So water is gonna come do acid base, or that negative charge is gonna do acid base right here, so we can make him a good leaving group later on. I think honestly, I don't know why, but he's gonna end up leaving, so I guess we're making him a good leaving group, because we would never want oxygen to leave with -2. Okay, I'm gonna draw it again. 1, 2, 3, 4. I'm gonna do it quickly. 4, 5, and so now we have this H here, and then we have oxygen with the H. So now I think it's our last step, or one more step. We're gonna be doing no. Now OH is gonna come in, and he's gonna take that alpha proton. He's gonna be doing, I think it's called like dehydration. Yeah, so we needed this second hydrogen to be there. so we could do this step. Remember right here we have two alpha hydrogens. Yeah, so the second alpha hydrogen is now being taken. We needed there to be two of them. If there was only one, it would not have worked out. So now put that charge on that carbon. And what we're going to get is, I think in one step, we'll do elimination. No more H, right? And then this is a ketone. One step, we're going to kick him out. We're going to make a bond here, and then we're going to kick the oxygen, not the oxygen, the OH out. And so it's going to go forwards, obviously. It's going to go forwards. The driving force for this is that we're making the double bond is conjugated with the ketone. The double bond is conjugated with existing carbonyl. I'm reading straight off it. Okay. So now this is our answer, and we have a ketone. And then obviously regenerate the base catalyst. Base catalyst regenerated. I'm gonna try to find more problems like this. This is low key, and it's not a hard problem. It's just I'd rather see more examples. I feel like there's always like, okay, what if there's a six-membered ring or freaking five, or you know what I mean, right? I feel like I want to know how to do it with the six-membered ring. Whatever, it's fine though. We're finally done. Let's play this took mad long.